So hello everyone, a very good morning to all of you, and thank you for joining the session on a Saturday morning. So I am Syed Mustafa Kazim, Associate Head, PG Academics Wing, Academics and Career Council IIT. So as have already been circulated to you that today's workshop will be held in two sessions. So we are starting the first session that would be from 11 a.m. to 1 p.m. And then we'll continue with the second session that would be from 3 p.m. to 5 p.m. So in session one, the speaker would be covering the following topics. So introduction to MATLAB, and then ODE solving with MATLAB, building apps with MATLAB, and then solving ODEs with Simulink and Simscape. So that would be if time permits. There is enough time for that. So let me take some time to introduce you to the speaker. So on behalf of the whole student community at IIT Kanpur, I'd like to welcome Dr. Dhruv Chandel. Dr. Chandel is a senior engineer with the education team at MathWorks. So you all know MathWorks. They are the creators of MATLAB and Simulink. So he's based out of New Delhi and works with universities across India to support the adaptation of computational thinking and model-based design in teaching and research. So Dr. Chandel has over 8 years of multidisciplinary experience in mathematical modeling and simulation, control system design, robotics, artificial intelligence, and embedded programming. So he has previously worked as a researcher in academia as well as in industry. So we are very pleased to have Dr. Chandel as a speaker for today's session. So now without any further ado, I would like to hand over the virtual stage to Dr. Chandel. So Dr. Chandel, the stage is all yours.
Thanks a lot, Mustafa, for the invitation, and thank you everyone for attending. We'll try to make this a really interactive, interesting session for all of you. Let me start sharing my screen. So also on the call is one of my colleagues, Vipul, and he will be handling some of the Q&A part of it. So you can put your questions in the chat and we'll get to them as time permits. So first, let me just find the controls for sharing the screen.
Yeah, so hey everyone, I'm Vipul, and just one quick reminder, please ensure that you select the tab to everyone when you send your questions in chat so that everyone can see it. Yeah, thank you.
Yeah, great, thanks. It says screen sharing is disabled. Could you give me the permission, please?
Sorry for that. Just a minute. Are you able to do it now?
Let me just check. 1 second. Please let me know if that comes up properly.
Yeah, it's now visible.
Okay, perfect. So I'll keep my chat open on my second screen. So I'll look off screen if I have to do that. Yes, just answering some preliminary questions. So the session will be recorded. We will give you access to all the files. You should have already received the link. In case you haven't, I'll share it again. There is one request. We have a pre-session survey form. This will take less than 60 seconds. So I'm pasting this in the chat. If you can please click on this, it will open up a form that looks like this. So at the top of the form, there is a link to MATLAB Drive, and all the files you need from this session are here. Okay, so you can download the files, you can keep it, you can modify it, anything you want. And the second link there is to a page called MATLAB Academy. So if you are totally new to something, or if you can't follow it today for whatever reason, you can go to this page. I'll just open and show you. And there are a whole bunch of online free courses here. So stuff like starting with the basics of MATLAB, or starting with the basics of Simulink, etc., etc. And all of these are free. You can do them hands-on online, and after doing these, you get a certificate as well. Okay. So I'm just telling you for information. I'll repeat this once. So in this survey form, if you can please put, do you know the basics of MATLAB and programming? Do you understand ODEs? Do you understand curve fitting, optimization, what these things mean? And what would you like to get most out of this session? Because just in case we run out of time, then I might have to skip one topic. So we'll decide based on what you tell us. Okay. Right. So let me do the introductions quickly, then I'll get back to the survey form. We'll see the results, and then we'll get to the hands-on part. So Yeah, I've been introduced already, but I'll just tell you very, very quickly. So my background is in mechatronics engineering. I used to work in robotics research. So on the top, what you can see there is a robot with a camera on the end. And this is one of my test tricks. So we used to scan objects from various sides and reconstruct 3D images of it. This was more for medical or aerospace applications where you can't touch the part to take measurements. And then the second thing you see at the bottom is what is known as a wave energy converter. So you can actually harness the motion of ocean waves and turn them into electricity just by capturing the energy. So that was my career before. Now I work for this company called the MathWorks, where I basically help people use MATLAB and Simulink in more advanced ways because it is very helpful for science and engineering and research in general. Was that a question somewhere? I heard some noise. Okay, not I guess. There's a question, are we covering from the basics? More or less, yes. So we did ask people to do the basic on-ramp, but I'm assuming many people will not have done it. So we will start almost from the basics, okay? Just let me take 2 minutes to tell you about where these skills can be used because most people are not aware of it. So this company MathWorks has been created basically by engineers and scientists, and we are all engineers and scientists. We love maths, physics, technology, and our mission is to help you do your best work. Okay, so we are there to enable your research. And just a fun fact, if you've seen this logo before, this is actually called the L-shaped membrane. It's the solution of a partial differential equation. And we're quite proud that we're probably the only major company to have literally a mathematical symbol as the logo, because this is all we're about. It's computation, maths, physics. I will share these slides afterwards. You can go and read up about it if you want. And these tools that you're going to learn today, it's not just for academia. They're very heavily used in industry. So if you go and work for an aerospace company or automotive companies or energy production, so this was my background, or robotics or medical devices, these things are very heavily used in industry. And certainly the techniques that we will show today, how to solve equations, how to fit data, what is machine learning. Even if you decide to go with another tool at the end of the day, the techniques will be same. Okay, so what we would like you to learn is the tool as well as the mathematical techniques. Both of these are useful for you. Not going to spend too much time on it. It's not a marketing session, but just you might be interested to know that if you plan on working for any automotive company like Tesla or I don't know, Maruti in India or Honda or whatever it is. So all of the top 10 auto companies use these tools. And if you've ever seen the ECU, which is the electronic control unit on your car, the code that is generated to go onto that unit is generated through Simulink. So if we have time today, we'll show you what that tool looks like. Same for all of the top 10 aerospace companies. So Blue Origin, SpaceX, Boeing, NASA, blah, blah, blah. They all use these tools because they're very useful in designing the complex things that need to work in the real world. Okay. So if that excites you, then you're in the right place, and we'll try to help you get started with it today. Right, let me go and check the survey results, then I'll come back to this stuff. So we've got 73 responses. Let me just refresh this. I hope my audio is clear, by the way. Vipul, is it okay?
Yeah.
Yes, sir.
Yes, okay.
Okay, great. Sometimes I talk a bit fast. Just tell me to repeat if you don't catch anything. Okay, so do you know the basics of MATLAB? Okay, so about 1/3 of the people don't know. So that's okay. We'll try to show you some basics. But again, I will not go all the way down to the level of this is an integer, this is how you add, subtract. We're going to assume a few things because otherwise the session will be boring for everyone. Do you understand ordinary differential equations, which is like a mass spin damper system for today? So most people understand it. I will briefly explain it for the people who don't know about it. And I will share some training links where you can go afterward to read on it if you can't follow. Okay. Do you know what curve fitting means? Little more than half. Okay, so we'll explain curve fitting in detail. Very few people know what optimization means. Okay, so what I'll do is I'll try to spend some time here if possible, because as an engineer, if you want to work in any subject these days, even if it is like a data science subject, optimization is at the core of it. Okay. Many of you have heard of these terms: machine learning, deep learning, data science, AI. It all relies on the same techniques that we are going to look at today. So you have to understand optimization, and we'll discuss a little bit of it. Okay, just looking at the comments. Can we also analyze AC signals using this? Yes, but we're not covering that today. Please give us small assignments in between the session. Yes, so you will have all the files, you can run the files yourself. And everything is hands-on. This is not a lecture. You will have the files and you will run it yourself. Okay, please describe the ODE part. Yes, I'll do that. Okay, what do you want to see the most? Everyone wants to see optimization and machine learning and Simulink. Okay, so I'll decide if I'll show Simulink first. I might skip the apps part depending on your feedback. Okay, let's see how much progress we make. Okay, cool. So I assume that's okay. Right. So let me close this. Just give me 2 minutes and then we'll go straight to the hands-on part. So one question I forgot to add, which was very important. How many of you have installed MATLAB on your system or you have access to MATLAB online? Can you write yes or no in the chat? Okay. Okay, so I'm very happy about that. So everyone has access to the software at least. That is the important part. Okay, fine. Thanks. Thanks for doing that. I'll give you the files link again in 1 second. So most of you said you already know the basics, but what is MATLAB? It's a high-level language. So it is something that is designed to be easy for humans to code in. So if you think about languages like C++ or Java, they're basically low-level languages. You have to compile them and then they will run. They're closer to the machine code level. MATLAB is something at a higher level. And the code which you write is very easy to learn. It's very easy to write. The trade-off is that the speed is a little bit slower. But if you're an advanced user, you can actually convert MATLAB code to C++ code. And then you can have both the ease of use and the speed. The place where MATLAB is used is for development. So if you want to work with mathematics, if you want to work with graphics, you want to make plots of things, you want to filter signals, you want to solve equations, MATLAB can help you out a lot. Okay. So numerical computation, data visualization, developing algorithms, and then developing applications, all of this can be done in this language. I'm not going to say that it is the best at everything, but if you take all the tasks in aggregate, there are very few environments, in my opinion, which can do all of these pieces, even if they're not so great at specializing in one or the other. So that's why it's quite useful. The second tool we make is called Simulink. I'll show this briefly. So this is a different kind of tool. It's a block diagram environment. You basically don't write code. You connect blocks which represent mathematical functions. And you can model super complex systems. You can model an entire car, for example. You can model the engine, the drivetrain, the clutch, the brakes, the road surface, the driver, everything in one model. And then that model you can use to simulate and test various kinds of things like control systems or communication systems, etc., etc. So we'll try to show you a little bit after the initial thing. Okay. Just be aware that this exists and this is also made by us. So it comes at the same standard of documentation. What's the plan for today? So the first session, we'll just have a brief intro to MATLAB. Then we look at solving ODEs with MATLAB. So we'll start with the mass spring damper system. I'm hoping most people have knowledge of this. What I'll do is I'll go to Simulink first, and then the apps part will get to after that, because there was more interest in the Simulink side. Then in the afternoon session, we'll have a 2-hour lunch break. Then in the afternoon, we look at curve fitting. Probably we'll look at optimization first and then go to machine learning, because they're quite related. All of these topics are very closely related to each other. Okay. Some people are writing no lots of times. Okay, let me share the link again. So if you don't have access to MATLAB, what you can do is you can go to matlab.mathworks.com, which is just this link I'm putting in the chat. Just log in with your IIT Kanpur official ID, and you should be able to open MATLAB online from there. I mean, it's literally that simple. Provided you've made an account. If you haven't made an account, just make an account with your IIT Kanpur ID. You should be able to get access automatically. Okay. If you have trouble, let me know afterwards, and after the session, we'll help you get access. So for today, you can just watch the recording. Second thing we had is the drive link. So was the drive link shared with them? Just checking. Mustafa, if you're there.
Yeah, it was shared through mail. You can check all the students can check their mail. It was shared.
So I have it here. I'll just copy it again. Someone says you have R 2016. Is that okay? Not really. It's like 5 years old now. So you should get the latest version or use MATLAB online. We did specify in the prerequisites you have to do the on-ramp and get the latest version. Okay, so because 5 years ago, there is not so much content for machine learning. Several of the toolboxes were not so developed as they are now. So please get the latest version. Okay, for today, you can use MATLAB online as well. R 2021B is the latest version. 2021A is fine. Anything after 2019 should be okay for today. Okay, so this link, if you click here that I've just shared in the chat, you will get a page that looks like this. Now, if you're on the desktop version, you can just download this folder and you will get all the files. It's just 5 MB. If you're on MATLAB online, there will be a link here for you, and you will be able to copy this folder to your MATLAB drive. So when you open MATLAB online, by clicking on that link, on the left-hand side, you will be able to see all of the files. It will be in a folder called IIT Kanpur. Okay, so I'll introduce this properly in a second, but what you can do for now is just download this folder and unzip it somewhere. Or if you're on the online version, just there will be a button here. You can click on it, and there will be an option to copy the files to your drive. And then when you copy it, in the left-hand side of MATLAB online, you will get a folder that looks like this, IIT Kanpur. And when you go inside that folder, all the files will be there. And they will stay in your drive permanently after that. They won't get deleted. Okay. So someone says they're not able to download. Can you specify what the problem is? I'll just share the link again. In the online version, you can also download, but then you will have to re-upload it to use it in the online. So it's better just to copy the files. If there's a server problem, just wait 5 minutes. There might be too many requests. So just try after 5 minutes, okay? Yeah, if there's a server issue, just try after 5 minutes. All right. So we spent enough time, so let me open MATLAB and just talk about the basics for like 10 minutes. Hopefully by that time, people will be able to get the files. So this is what MATLAB looks like. In the middle, we have a command window. You can just put in some code here and execute it. On the right-hand side, we have a workspace. So all the variables you declare will appear here. And on the left-hand side, we can navigate to the folder. So only the files that are inside the current folder will get executed. That's just a safety feature, okay? If your MATLAB doesn't look like this, you can go to the Layout tab and you can go to the default layout. If you want, if you're comfortable with the custom layout, that's also fine. Okay. So just to show you why MATLAB is useful, let me just do some random calculations. Okay, this is not planned stuff. Let's say I say a equals 2, b equals 3, and I just have to write a plus b. So I can get the answer as 5. Now what you will notice is I don't have to declare a as an integer, b as an integer, compile the code, etc. I can just type the commands and it gets executed straight away. So 2 advantages: you don't have to declare the type of your variable. Second thing is you don't have to compile the code. It will run as you type it. Okay. I can use this home command to get the code up again. We'll just see. So if I type home, it will just bring the command line to the top. Okay, now let me show you another thing. So MATLAB stands for Matrix Laboratory. So what this software is built to allow you to do is you can create arrays and matrices. Arrays are linear vectors which have lots of values, and matrices are 2-dimensional, 3-dimensional, like that. And you can manipulate them directly. So let me show you by example. So let's say I say C equals 1, 2, 3, 4, 5, like that. And then maybe I want to double every element of this vector. So a vector is just a 1-dimensional matrix. Okay, so I can say C times 2, and that will double the whole thing. So these are what is known as vectorized operations. You will notice you don't have to write a for loop. Okay, if you have an array or a matrix, if you do any standard operations, all the elements will get modified in the same loop. So that saves you the trouble of having to write multiple for loops for doing your things. By the way, I'm hoping you can all follow this stuff hands-on. Another thing what we can do is declare, let's say, 2-dimensional arrays. So if I have d equals 1 space 2 space 3, colon shifts it to the next row. I can write 4, 5, 6, 7, 8, 9. This will create a matrix. This is a 3x3 matrix. And suppose I wanted to do the same kind of operation. What I can just do is, or let me do something else. Let me say d dot square. So this will square every element of this matrix one at a time. So this is an element-wise operation, and we're applying the power 2. So again, you will notice that I have a 2-dimensional matrix. I have rows this way, columns this way, but I don't need to write 2 for loops to do this operation. I can just write it in 1 line of code, and the operation will execute. Okay. So this is the advantage of having a higher level language compared to a lower level language, that you can develop things extremely fast. You don't have to spend a lot of time writing a lot of code. Okay. Does everyone follow so far? Could you please just write yes or no? Or if there's any questions, just ask. I'm seeing mostly yeses, so that's okay. Yeah, just check the files link if you can download now. I'll put the drive link again. And we'll show one more thing, then we'll get to the files. Okay, there's a really good question. What is the difference between d dot square and d squared? So let me show you. So first, if I output d, this is a 3x3 matrix. So there are 2 things you can do with a matrix, right? Either you can multiply the matrix to itself, or you can element-wise square each of these. So if I just write d square, what is going to happen is this 3x3 matrix multiplies to itself. So then you have to, multiply every row by every column, and then assign all the pieces in the individual places. So d square is going to give you this answer, and d dot square is going to just square each of these elements individually in their place. Okay, so this is just a very nice, convenient way of separating what is a matrix level operation and what is an element level operation. Does that answer the question? Is the question, can we do matrix multiplication? Yes, exactly. So let's say I have, let me make two more matrices. So I have D anyway. Let me make another matrix E equals some random numbers 8, 5, 4. Okay. So first of all, let me multiply E times D. So this is a 3 cross 1 matrix. D is a 3 by 3 matrix. So I can multiply this. Now, if I try to multiply these in the reverse way, D cross E, you will notice it will give me an error, right? Because the inside dimensions have to match in a matrix multiplication, if you remember. So I can't do this. What I might be able to do is take the transpose of E. So the way you take a transpose is just put an apostrophe on it. So if I say E apostrophe, this will convert it from a row into a column. Now this I might be able to multiply. Let's check. E cross E column. Okay, so that actually gives me a result. So like this, you can do operations on these matrices very, very easily. You can take the transpose, you can get the inverse. You don't have to spend a lot of time solving stuff. And if all of you have studied your linear algebra, then what you know is a matrix is basically just a system of equations, right? So with one line of code, you end up solving a whole system of equations. That's what these operations actually mean. Could you please teach how to handle 3D matrices? Yeah, it's actually fairly easy. I think I'll have to look up the syntax for 1 second. So if I want to declare a matrix of a particular size, which is just random, I think there is this command called rand, R-A-N-D. Now, I don't remember the syntax for this. So what I will do is I will type doc, D-O-C, and then rand. What this will do is it will open up the documentation, and then I will be able to see the syntax from there. So the documentation is a very, very powerful thing to understand in MATLAB. If you know how to use the documentation, you will be able to solve like 90% of your problems. Now here I can see various ways of calling this function rand. Okay, so either I can say x equals rand. This will return a single random number. If I write random of n, it will return an n by n matrix. If I write more numbers here, it will return me a matrix of the size that I've specified. Okay, so let me make a maybe 3 cross 3 cross 4 matrix. Okay, so I can say x equals rand of 3 cross 3 cross 4, and this will give me a matrix which is 3-dimensional. Size 3 in x, size 3 in y, and a depth of 4. Okay, so I will get, this is the first layer of the matrix, second layer, third layer, fourth layer. Like this, I can see everything. Now, if I want to access any of the dimensions of this array, I use the same syntax, x open bracket, which level do I want? Let's say I want the first row. Maybe I want all the columns, and I want the second layer in depth. So I can write this, and it will just allow me to access that particular row or that particular column. Okay. So this way, you can manipulate all the basic matrix operations. Now, for those of you who have never done any MATLAB or any programming before, we did set this as a prerequisite. I was hoping people would do it. So you should go to this page and complete this MATLAB on-ramp. So this is a 2-hour course. It runs online. And this will basically take you through these fundamental activities that you can do with the software. And if you want more detail, then there is a longer course, 25 hours MATLAB fundamentals. So after this, you can do the second one if you want. So I'll just copy the link and share it. You can do it afterwards. Okay. Fine. If you can't download the folder, just check with your friends, because I think most people have been able to download it now. Can we see a yes, no again in the chat? Who now has access to the files? Okay, so I see most people are able to get it. By chance, if you're having trouble, just check with your friends afterwards and get a copy of the files from them. Okay, right. So let me just show two more things quickly, then we'll move on to ODEs. So you will notice in the workspace, I have a lot of clutter now. I have all these random numbers. I don't want this in my workspace. It's taking up memory. It's distracting me. So I can use two commands. I can use clear to get rid of everything in the workspace. And if I don't even want to see that command clear, I can type CLC and that will clear my screen. So it will just get rid of the commands. Okay, so these two are nice to know. Now, oh, there's a question how to upload the files in MATLAB online. So let me try to open this in incognito mode, see if it works. Basically in MATLAB Drive, if you look in the top left-hand corner, there will be a button here. If you click on that button, it will say copy files to online drive or copy files to your drive. You have to select that option and then it will automatically appear in your MATLAB Drive. Okay, the reason I have not put it in a Google Drive link is because you will still need to re-upload it for MATLAB Online. But MATLAB Drive is integrated, you will access it directly. So that is why I've shared in the MATLAB Drive format. So just try to do it from this top left-hand corner. There should be a button there that says copy files to folder or copy files to drive, something like that. If you're having trouble, just observe for now. And in the break, then you can get the files from me. Right. Okay. So a couple more things. We'll show this very quickly and then move on. So how to call functions and how to create vectors. So let's say I write time equals 0:10. This will generate a uniformly spaced vector of time. And suppose I want to generate a sine wave over this time. So I can say y equals sine of time. So this mathematical function will also work on a matrix or a vector. And I don't have to apply a for loop to go through all of this again, right? Now, suppose I want to plot these two things. So I can just say plot time comma y. Or I can even plot time of sine comma time. And if I use this plot command, the syntax is first the x numbers and then the y numbers. You will see a figure pops up. Okay, and that's what it looks like. So I have time on the x-axis and I have the values on the y-axis, and this generates a graph for me. Okay. Could anybody tell me what is the problem with this? Like this doesn't look like a sine wave to me.
Gap between numbers are large.
Values are less.
It is not continuous, sir.
It is not continuous. Okay. So one thing to understand is in the computational world, nothing is continuous. Everything has to be numbers. So we can only approximate continuous functions. Okay. Unless you're using symbolic maths, which is a different thing altogether. So if I plot the markers on top of this curve, like this, you can see the gap between the points is too large because 10 seconds I took for time and I'm sampling once every second. So what I need to do is I need to have more samples. I need to reduce the space between the times. Okay. So how do I do that? I'll just say time equals 0 colon spacing of 0.1 colon 10. And this will generate a much finer gradient. A much finer spacing. And if I do the plot command again, now you will see I have a nice smooth sine wave. Okay, so this is how it should be. So 3 things we've learned here. One, you can create vectors with uniform spacing in just that one line syntax. Second thing we've learned is the spacing between the points matters, because if you want to get a smooth curve, you have to have the spacing small. And the third thing was you can generate plots by using the plot command, supply the X points, the Y points, some syntax for markers, and this will give you nice plots. And then later on, you can add labels and export these and all that stuff. So I'll show you that. Any doubts so far? Any doubts? Sorry, could you repeat that?
Sir, actually, it says that plot is not supported.
What is not supported?
Execution of script plot as a function is not supported.
Can you just
command.
Yeah, so are you on MATLAB online?
No, offline.
Okay, can you just check the syntax is correct? So the syntax should be like this. Okay, I'll just repeat the commands here, and I'll also copy them in the chat so you can follow. So I'll say time equals 0, 0.110. Then I'll say plot time comma sign of time, line with O markers. Okay, so this is the syntax. If you literally copy and paste this, this should work. Just remove the 2 arrow signs before this. All right. Let me just check the comments.
Sir?
Yeah.
So what is that -0 or the syntax?
This thing, yeah. So in the plot command, there are various kinds of syntaxes which are available to us that will let us change the properties of this line. Okay. So if I type dash, that means it is going to be a solid line. If I type O, that means these O markers are going to appear. Okay. Now suppose I want to plot another line on top of the same graph. Let's say it's a cosine function. So first thing I will do is I will say hold on. That will just hold the data that is on that graph. It won't get overwritten. Now let's say I say plot time comma cos of time comma, let's make it a double dash line, X shaped markers and in a red color. Okay. So these things you can get from the documentation. I'll show you how. And if I look at the plot again, you will see this. So the second line that we have plotted is red color because of R keyword, that key letter. It will have X shaped markers and it is going to be a dashed line. So that syntax I specify after the plot command that will change how the graph looks. And this is very useful when you have 5, 6, 7 things you want to plot on the same graph. Another thing we can do is we can put a legend on it. So I can say legend sine comma cosine. And when this legend comes up, you will see the graph is now labeled with that. So I can put it down here. Now, I'm just going to give you a couple of pro tips here. So these were extremely useful during my PhD. You might also find them useful. So number one thing is you can go to tools and then you can click on edit plot. Okay, so this will open up the plotting functionality. Let's say I double click here. An entire separate menu will open up that will allow me to customize each and every part of this graph. I can change anything I want. Okay, so it will just take a minute to open up the first time. And then instead of worrying about what code should I write to change the graph, you just modify it in here. So let's say you want to change the font, you can just change the font of this graph. Let's say you want to put labels. Okay, so let's say on the X label, I just want to put time in seconds. Okay, so I just modify that, the X label will appear. I can go back, I can change the Y label. let's say I put it as signal, maybe in volts. Okay. I'm just making this up. I can put a title, I can put a subtitle. I can change the styling of this. I can do all sorts of funny things. I can turn on a grid if I want, whatever. So let's say I click on grid. I can add an X and a Y grid. Okay. I can change the background color if I want. So this edit plot functionality is very, very useful. Second thing, let me tell you, is you can save the figures as well. So if you go to File and hit Save, this will save the figure as a MATLAB.fig file. Another thing you can do is you can click Save As. And after you click Save As, let me go into the IIT Kanpur folder. So instead of saving as a figure, you can also save it as a .eps file or a .png file. So what will happen is, suppose you're writing your thesis in the end, you can just have these figures saved as .eps files or .png files. You can call them from LaTeX if you're using LaTeX, and these figures will appear as nice, clean, transparent, well-formatted things. Okay. So let's say I save this as a .png file. It will be exported, and then from my IIT Kanpur folder, I can just open this as an image. So this image you can put in any other document. Okay, so these are like 2 pro tips. I'm just telling you, it will save you a lot of headache. After, yeah.
The property inspector.
Sorry, could you repeat that, please?
Can you repeat the property inspector tool, the advanced tool you said just?
Yeah, so you just have to go to tools and then click on edit plot, and this thing will appear. Okay, so tools, edit plot, and then maybe just double click on a line somewhere so that it will appear on that side, left side. So let me just close it and show again. I've clicked edit plot. Let's say I double click on this line. So it will just appear on the left side with the line selected. Okay, does that work?
Yes, thanks.
Okay, great. People who have missed this, please come back and see the recording, because we are like almost halfway through the first one and I haven't even gotten to the ODEs yet.
Yeah, I would request all to ask as many questions at the end. So you are lowering down the pace. So yeah, recording would be helpful. We'll be sharing the recording links later after this session. Thank you.
No, I mean, questions are okay, but it's just we have to keep the pace up because we have to complete some stuff.
We're falling short of time. Yeah. Thank you.
Thanks. So if you missed something, you have to go back and watch the recording most of the time. Okay, cool. Right. So let me clear all this stuff and get to the main point of today. So if I go into the IITK MATLAB folder, I have a slightly different one because I have some more files. I want you to open the mass spring damper folder, please. Okay. I'll open it on MATLAB online for you as well. So if you're inside the IIT Kanpur folder, just go and open this mass spring damper. Double click on it. Okay, don't click on the arrow and just see the files. You have to double click and go inside the folder. If you just put the down arrow, it won't run the files properly. So inside this folder, what I have is a whole bunch of files. And what these files are doing, I will just tell you, we will not go through all of them, but I have 8 or 9 different methods here to solve the same problem, which is the mass spring damper problem. Okay. So these are just given to you for reference. I will tell you what is here. So in the MATLAB 01 script, we are going to solve this ordinary differential equation using analytical methods, using symbolic maths. In the second one, we are going to write our own numerical solver. In the third one, we are going to call one of the inbuilt solvers, ODE 45. Fourth one is using ODE 45 plus symbolic math. So we'll skip this one. It's not so important. Fifth one is an optimization demo. Maybe I'll show this in the second part. Okay. And then we have Simulink models. So we have a Simulink model. Then we have a model for controlling it. And then we have one for Simscape. And then we have a couple of apps as well, which can do everything. So all of the methods that you could possibly need to solve this problem are here. The key is to understand first the problem and then the methods. So first, let me talk you through the problem. So just go to this live script ML01 MST analytical and double click it.
Sir, sorry to interrupt. Can you please spend 2 minutes and tell us where the files are? I am not able to find these
Yeah,
files.
so have you got the IIT Kanpur folder? Did you download it?
So I have reshared the links in the chat. So if anybody wants the files, they can go through the link.
Okay.
Sir, I'm trying to access the drive link, but it's saying permission denied.
No, I'm pretty sure I've shared it. So if you
So
click on
it's
that
a-
link, you should get this.
Sorry to interrupt. It's a 5.5 MB, so you can call on one of your friend and just have the zip file through your email it. Like it's a 5.5 MB file, zip file.
Okay.
Call on your friend, one of your friend, and get it through it, email or Gmail, anything.
Okay. Yeah, thanks for that. I'm sorry, I don't know why we have server issues today. It's fine on my side. Anyway, through that link, you should be able to download it. Otherwise, get it from your friends. Okay. So after you unzip that folder, IITK MATLAB, inside it, there are more folders for different parts of this workshop. And we are inside the mass spring damper folder. Okay. And the script you should open now is the ML01 MST analytical script. So this is an analytical approach to solving that problem. Stop this. Okay. So when you open this live script, it's a .mlx file. So many of you will have worked with .m files. This is MLX, meaning it's a live script. And a live script will allow you to have text, images, equations, and code, everything in the same format. So this is kind of the modern way of using MATLAB. This is what we recommend these days. So we'll just show you how it works. The coding is exactly the same as before. It's just a few formatting things are given. So if this live script opens up for you properly, and it should, then just double click on this blue bar and it will maximize it. So it will take up your whole screen. Now, every time you plot something or you get an output, you don't have to switch screens. Everything will appear in the same screen. That is why this has been built. Now, the problem statement for us right now is this mass spring damper system, how to solve for this. So what a mass spring damper system is, assume you have some surface and you have a mass a little bit away from the surface. It can be a block. Now it is connected to that surface by a spring of coefficient K and of a damper of a coefficient B. So a spring is something, if you displace it, it will try to pull back to the original position, right? That's what a spring is. I hope everyone understands it. What a damper does is, if you move the block, it will resist the motion. It will resist the velocity. So a damper is basically like friction. The faster you move, the more energy you lose. And if you're just sitting at one place, it will not apply any force. Okay. So effectively speaking, this is like the suspension of your car. Because you have a mass, you have the surface of the road, in between you have your suspension. So inside your suspension, you have a spring. Sometimes they have plates as well. And you also have a certain kind of oil type cylinder, such that your car will not keep on vibrating. The oil actually dampens out the vibration. It reduces the vibration. So this is a very, very practical problem. It is used everywhere. It's in your car suspension, in your motorbike suspension, in the landing gear of an airplane, inside robots. So the hinges of a robot are like this. Your muscles and bones behave like this in many circumstances. So it's a very, very common system. And it's also typically the first one we try to take as an example. Okay. So we'll just fix everything on this one system today, and we'll see many examples of different ways of solving it. You can just as easily take a DC motor or some other circuit. I mean, that doesn't matter. The techniques are the same. Right. So what are the equations of this? So if I displace this mass by a distance of x, applying a force of F, I can use Newton's second law. So mass times acceleration equals the sum of all forces. And acceleration is nothing but d2x by dt squared, right? So I can say m times d2x by dt squared equals F, which is the force, minus kx, which is the spring force that is pulling it back, minus b dx over dt. So dx over dt is the velocity. The damping coefficient times the velocity will also apply a force against the motion, right? And then we use this dot notation. So however many times you're differentiating it, you just put a dot on the top. So we say mx double dot equals F minus kx minus bx dot. That is the system of equations that we're trying to solve. So this is a second order differential equation because that's a second order term there. And what we typically do is we supply these parameters. We tell what is the mass, what is the damping ratio, what is the spring coefficient, how much force are you applying, what is the starting position. And once you supply all of those things, the computer will solve the equation and it will tell you how the system is behaving. Okay. So for example, what I like to imagine is, imagine I have a car driving along and it goes over a speed breaker. So speed breaker is kind of like a step input bump. So what will happen after that? Will my car just keep on vibrating up and down? Or will it settle down very quickly? Or will it be a very stiff response that all of the force of that speed breaker goes through your body? So we need to tune the parameters properly of this. Okay, fine. So the way we operate in this live script is we typically use this run and advance command. So if you see these blue lines, which are between the different sections, the code is split up section by section. So you will run one section at a time. So you don't have to run the whole script if you change only a piece of it. Or you can click this blue bar on the left-hand side, and that will also execute the code. So you can either just scroll down and keep on clicking the blue bar, or you can just run in advance. Run in advance is usually easier. So I'll just click here. First, I'll clear the workspace and clear all of the outputs. And then in this section here, on line 4 of the code, I'm going to define some parameters. So I'm going to say mass equals 10 kg, spring coefficient is 1, damping ratio is 1, and I'm putting in an input force of 10 newtons in this equation. And I can run this section. Now, what happens here is everything that is within these gray colored boxes, that is code. So that will get executed and it will have a line number associated with it. But let's say I want to write some more text here. So I can just go and click on the top, this text button, and it will convert that line into text. And then, I can write anything here and it won't get executed. Okay, so I can just run this piece of thing, this code again. This line will not throw up any errors. Now, suppose I want to go back to the code world. I just click code. But you can see this is highlighted because this will give an error. This is not proper code. Okay, so if you want to write comments in the code, we use a percentage sign. So whatever is followed by percentage sign is a comment. It won't get executed. Otherwise, we just turn it into text. Okay. Another thing, how do we get this control from? So this slider control is there. So in a live script, you have many of these. If you go to the insert tab and go to the tasks or the controls, you can put in a lot of controls. You can put in sliders or drop down menus or boxes or buttons. You can put in a lot of this stuff. We're not covering it in detail, but you can explore in your own time. There are also tasks. So you can automatically load data, clean, smooth, do an optimization, create a plot. Lots of these things are automated now. So the process of writing code is a lot less painful than it used to be 5 years ago. Okay. Cool. Is everyone able to follow me until line number 7? Could you please type yes or no? Okay, someone is saying how to create sections. Yeah. So after putting yourself on any line of code, you can go to live editor and you can insert a section break from the live editor tab. So this will generate a new section for you. Someone is having trouble in output. If you're on MATLAB online, just close it once and start again. Sometimes there are problems in MATLAB online. On the desktop version, I hope it should be fine. And if you have a problem in the comments, I'd appreciate you write what the problem is. If you just say, no, I don't really know what your issue is, so I can't solve it. The question, what is the difference between clear all and clear? It's the same thing, more or less. Clear all is an older syntax. I just write this out of habit. Clear will do the same thing. Okay, close will close all the open graphs. That's what it does. Okay, once I get to the end, I'll tell you why we are using live scripts, because it makes a lot of headaches much easier. Anyway, what we're going to do now for the next like 5 minutes, we are going to solve this using symbolic maths. So there is a toolbox for symbolic maths in MATLAB. Our job today is not to understand the symbolic math part of it. There's a separate training on that. You can do that afterwards. Our job today is to understand how the system works and how solving ODEs works. Symbolic maths is useful for certain kinds of problems. I think it's much more useful to understand how the computers actually work with these problems. So what we're going to do here, first we're showing this because it's very similar to the pen and paper approach. Okay. So I declare a symbolic variable called x as a function of time using this command called sims. So MATLAB will understand that x is a variable which varies as a function of time. And then I can also differentiate this. So I can say dx equals differentiation of x. And then my entire ODE on line 10, this becomes ODE equals mass times differentiation of x with respect of times, mass times differentiation of x with respect to time of the second order. So this is d2x by dt squared times damping ratio times, plus damping ratio times dx plus kx minus f equal to 0. So this is how you define an ordinary differential equation using symbolic maths. Then we can set some initial conditions. I'm going to remove the semicolons here, so you will see the output on the right side. So I will say at a time of 0, x equal to 0, which means initially there is no displacement. At a time of 0, the dx equal to 0, which means there is no velocity at a time of 0. It's just sitting there and it's waiting for a force to hit it. What I can do is I can get some analytical solution using the dsolve command, and then we'll be able to plot this over 100 seconds. So let me just run this. Symbolic maths is a little bit slower than numerical solutions. But what you will see is we are able to have this equation. This is the ODE. We apply the initial conditions. We get the analytical solution here. And then I can plot the displacement of the system. Okay. So what this means is my suspension of the car was sitting there happily enough, no problem. Suddenly it was hit by a force of 10 newtons. So it displaced. Okay. It went from 0 and it went all the way to 15 meters. So these units are just nonsense. You can imagine if it's centimeters for now, because the values are too small. So it went to this huge displacement. Then it came back down because the spring is pulling it back down. And slowly it keeps on oscillating and losing energy. And eventually it settles down after 100 seconds. Okay. So if I have a system like this, which is a mass spring damper system with a very low spring coefficient, with a very low damping force, and I just apply a small force to it, I just hit it, it will show this kind of response. It will go to a huge displacement value, come back, oscillate again and again, and eventually settle down. The oscillation happens because of the spring force, And this reduction happens because of the damping. It is losing energy constantly. Okay. Okay. What are the doubts so far? Let me just check. I'm sure many people will have doubts. Okay, I'm just scrolling up. There were a lot of comments. Can you please go a little bit slow? Many things are new for us. I am going fairly slow. I mean, after 1 hour, we've gotten to this point. You were supposed to do the on-ramps. That was the prerequisite. So we have to cover this stuff. Otherwise, we won't get through the whole session. You can come back and watch the video again if you're not following. Okay. Difference between single equal to and double equal to sign. Yes, that's a good one. So the single equal to sign is an assignment operator. It takes the whole equation and it assigns it to that variable. The double equal to sign actually is a way to test the equality. So it will say this part of this expression must be equal to this part of this expression. And this entire equation that we have gets assigned into this variable ODE. Okay. So similarly, we will say condition at x naught equal to 0. That's the equality that has to hold. And this entire equality statement, we assign it to a variable called condition 1. So that is the difference between the two of them. It's okay if you don't follow the syntax of this part. The purpose of this part is not the syntax. The purpose of this part is to understand the problem. We'll do it using different syntax in a minute.
So while I'm running this file, I am getting an error of adding symbolic toolbox. Sims require symbolic toolbox.
Okay, so I did ask people to install all the toolboxes. So if you haven't installed all the toolboxes, you will run into errors multiple places. So what you can do is you can go to add-ons, get add-ons, and try to get the symbolic math toolbox from there. Otherwise, run on MATLAB Online because MATLAB Online has all of these already. Okay. By the way, I will always recommend all of you install all the toolboxes because it is only like 25 gigabytes and it will save you a whole lot of headaches because when you need a feature, you will have the feature. Otherwise, you won't know what you're missing out on. Can you explain the desolve command? Yeah, so this is just a command that solves a given ODE in the symbolic maths toolbox. Don't worry too much about this. I will show you the details of how the solution actually happens numerically. This is just a syntax for this particular toolbox. So don't worry about the syntax part right now. Okay, sir, I'm changing inputs, but output is not changing. Right, so it depends on what outputs you change. Okay, so suppose this was the suspension of my car. Now, one thing to understand is if f equals kx, that will give you the settling point of where your displacement is going to level out at, right? So when all the kinematics die down, when all the motion dies down, your f equals kx is the equation that tells you what the displacement will be. It doesn't have a mass term. So changing the mass actually doesn't make that much difference. It's just inertia. What will change this curve is if you change the spring coefficient, number 1, and number 2, if you change the damping ratio, or number 3, if you change the force. So let us imagine the mass and the force is fixed. Because if you're building a car, if you're building an airplane, typically you can't change the mass that much. And you also can't change the force that much. Because the force will be a result of whatever input is coming from outside. The mass will be a result of whatever the device is built out of. It is rare that you can change these things. But these two coefficients, the spring and the damping, this is what an engineer has control over. Because I can go and select a heavier spring, I can go and select a heavier damper, right? So if I have this kind of system, first of all, it's totally ridiculous that I have a displacement of 10 meters, right? My car hits a speed bump and I'm flying off into 2-story building kind of height. So what is the first thing I should change? What is the first parameter I should change here? That's the question.
Displacement.
Units.
Okay, so you can't change displacement. Displacement is an output of the system.
The spring constant.
Spring coefficient.
The spring coefficient. Again, someone is saying mass of the car. You can't change the mass of the car. Car weighs 2000 kilograms. You can add or subtract few kilograms. You can change how strong your spring is. Okay. So the task here is to understand what is the problem, what is the things that are under your control. You can't change the mass that much. You can't change the outside environment. You can change the spring resistance. So let's say I make this 10 times bigger. My spring is now 10 times thicker. And I run this whole code again. What I will do is I will go to live editor and just run to end. Okay, so now the shape of my graph will change. Okay, this is interesting. So instead of going to 10 meter displacement, I'm now only going to 1 meter displacement, which is still huge for a human body, but it's not crazy. It's not like the height of a building. But now what you see is there's a lot of oscillation, right? So imagine if I'm sitting in a car, I'm actually bouncing up and down because this oscillation is driving me up and down, up and down, up and down. This is crazy. It's going to break all the components. It's going to cause damage to me, right? So what do I need to do here? What's the second thing I can change? Any ideas?
Damping.
Increasing the damping.
Yeah, so the second thing I can change to reduce the oscillation is I can change the damping ratio, which is this guy here. If I convert this into electrical analogies, if any of you are from an electrical or physics background, so the damping is equivalent to having a resistance. And the spring is equivalent to having a capacitance to an electrical circuit. Okay. So if I want the energy to be dissipated more quickly, I want to add more resistance, I will increase the damping ratio. So I increase the damping ratio by 10 times. Again, run to end. And what I see is actually a very nice output. So my car goes over a bump, it just settles down after 1 second. This is a nicely engineered system. Okay. Yes.
In my system, the output is not changing.
Okay, so you have to run all the way to the end. Okay, so you have to run to end because all of the sections of the script have to run.
Okay.
Okay. Right. So, first of all, does this make sense to people what we are trying to do here by solving these problems in a computational manner? Just ignore the syntax of the symbolic math toolbox. That is not important. Do you understand what is the task we are trying to do here as engineers? Can anyone summarize or write in the comments or whatever? Not exactly optimization, close.
Maybe changing the input parameter and directly getting the output parameter, not solving the equation rigorously.
Okay, I got half of that.
Like changing the input parameter and getting the output parameter directly, but and not solving the equation rigorously, like obtaining root 3 and all. It will be very not easy.
So by using trial and error method, you are calculating which spring is like what would be the damping coefficient. It would be suitable for the system to be in stability.
Okay. Okay. So some nice answers here. So let me summarize all of that. Okay. So my job as an engineer, what is it? My job is to design some machine. That machine has to work sensibly, right? Now, in my theory classes, in my second year, third year of engineering school, they taught me the theory of all of these equations. So you will have learned, oh, this is a second order ODE. This is a first order ODE. This is the response that comes out of the second order ODE. And all of you, you are at IIT Kanpur, you are fully capable of solving this equation. The point, as someone mentioned, is do I have free time that I'm going to sit here all day and crunch these numbers by hand? No. This is not my job, right?
No,
or it is my job, but I don't have time to waste here. So what I want to do is I want to program a computer such that the computer can do the heavy calculations and I just tell it what to do. Do you understand that part of it? Yes or no? Okay, this is why we are doing all of this stuff. Okay, everything else is following up from after that. The job of a computer is to make my workload lighter. I'm not doing this just for fun, even though it can be fun. I'm doing it because suppose that I had to test out 10 different springs and 10 different dampers for my system. Okay, because you will go to a shop and you will say, hey, what size spring do you have? It will give you 10 different sizes in the catalog. What size of damper do you have? 10 different sizes. So I will have to run 10 times 10, 100 times this equation. I have to solve it. So I'm not going to sit there and crunch the numbers myself. I'm going to feed it all to a computer and say, you give me the results. That is why we do all this. Okay. So exactly what many people have said, we are changing these parameters and we're trying to find out what is the best configuration for our system. And by using a computer, what I do is once I set up the solution, I can just keep on changing the parameters and I can see the output. I can select this is the right size of system that I want. This is exactly what you will do in your PhD research as well. You will have to show how you solved the problem. You won't have time to sit and calculate all these by hand. So this is why we should know how to solve these equations. Okay. Cool. And we're also getting graphical interpretation for the various outputs. Yes, exactly. So I can see on a graph what is happening. Okay, cool. Right. Any more questions or comments about the exercise as a whole at this time? Not about the specific syntax. No? Yes, okay. Okay, so I assume we are fine. So if you want to learn more about symbolic maths, again, go to MATLAB Academy. There is a section called Math and Optimization. Okay. So inside here, there's a course on optimization. There's a course on symbolic maths. There's a course on solving ordinary differential equations. All of these are free for you, by the way. And it also tells you how much time it will take. So I guarantee you, if you spend 4 hours here or 5-6 hours here, it will save you 6 months of your PhD. I guarantee you this, if you're following the process properly. So that is why it should be helpful to you if you can just go here and maybe try out a few of these. I'll put in the link in the chat. There's a limit to how much we can explain in a session, but if you do the courses, you will understand all the pieces. All right. Okay, so the second thing here is, let me close the script. The second thing to understand is how are these ODEs solved? And how can I write my own solver in a way that I understand? Because the symbolic math stuff is too complicated, right? It's too abstract. So what we will do is we'll open up this next script, ML02, the numerical solutions of a mass spring damper system. And then I will show how this solution actually comes. Was that a question? Okay. Does everyone want a 5-minute break if you're getting distracted? Just type yes or no. Okay, people are okay for now. Yeah, let me do this section, then we'll have a 5-minute break, okay? Because the last part is complicated, so we need everyone to be paying attention. So just hold on for 10 minutes, then we'll have a break. So next, what you can do is close that script and open up the ML02 mass spring damper numerical solution, okay? So by chance, this equation that we were solving, this mass spring damper equation, this has an analytical solution. You can actually write out the mathematics and get the solution out. But for most of the problems that we solve, there is no analytical solution. You actually cannot derive an equation that gives you the solution. Okay, this MATLAB logo that I had shown, excuse me, let me just tell you the story of this now. Why we have put this logo here, there's an actual reason for it. So if you take, sorry, not the right link. Okay, so if you take something like a square domain and you clamp one end of it. Okay, so suppose I have like a handkerchief. This is, imagine this is a vibrating plate and I clamp one square of it. And then I try to figure out how the vibration is happening. What you will find is you by hand, you cannot write out a solution. It has no analytical solution. So then what we need to do is we need to numerically calculate each of these points, how it is going to behave if I put a force there. And there are some mathematical techniques to do that. They're called partial differential equations. So the solution of this particular problem was the PhD thesis of a guy called Cleve Muller, who wrote the first version of MATLAB. And that's what this membrane actually is. So if you have a square and you clamp 1/4 of it and you vibrate it, this shape is the first vibration mode. Okay, so the reason we have selected this is a problem which you need a computer to solve. You won't be able to solve it by hand. That's the story behind it. But let me show you a simpler problem that we can program a computer to solve. Okay, so we have the same mass spring damper problem. This is an ordinary differential equation. We already know what it looks like. How do I actually solve it? Could you mute, please? I think Naman. Okay. So again, in the first two sections, it's the same thing. We clear the workspace, define the parameters, same parameters. But how does these numerical solutions of this ODE work? Okay. So suppose we have the same equation, mx double dot equals f minus kx minus bx dot. The only way you can solve the second order ODE or the most convenient way is to break it down into two first order ODEs. Okay. How do we do it? We break it down into acceleration velocity conversion and then velocity displacement conversion. What does that mean? So if I know the acceleration of a system, how would I get to the velocity? Can anyone answer?
By integrating it.
By integrating it, right? So if you have acceleration, if you know the acceleration of a system, all you have to do is integrate that value and that will tell you what the velocity is. Okay, so that is one ordinary differential equation. Okay, now suppose I have the velocity of a system. How am I going to find out the displacement?
Again integrating it.
Again integrating it. Okay, so if I know what the velocity is, I integrate it again, that gives me the displacement value. So this is what this section is telling us. Instead of getting confused with a second order system, because you can't add or subtract a second order system, we break it down into two pieces. One piece is the displacement piece and the other piece is the velocity piece. Okay, so instead of this value x, what I will do is I will substitute it with some variables x1 and x2, which store the displacement and velocity respectively. Okay, so I will say if in this equation I have a value x, I am going to substitute it by x1. And if I have a variable x dot there, I will substitute this by x2. Now I know that x1 dot is equal to x2. Okay, because x1 is my displacement. If I differentiate displacement, I will get velocity, which is x2. And here is the neat trick. If I differentiate x2, which is my velocity, I will get x double dot, and I can just substitute x double dot with the rest of this equation. Okay, so this equation actually becomes, I'll just write it down here. Just copy this. So if I just eliminate this second order piece here, this, if you look at what this equation is, we have artificially converted it to first order. Okay, because there is no term here which has 2 dots above its head. So if it's a first order ODE, I can actually solve it using a computer. Why? Because all I have to do to integrate something is add the value, right? Integration is just addition with very, very small pieces. Differentiation is just subtracting the last value and dividing by time step, right? If we approximate at the very small time step. So addition, subtraction, these are operations that a computer can do. So integration, differentiation, we convert them to addition, subtraction, and then we can solve this equation. Does that make sense to people? Yes or no? Okay, if this piece conceptually makes sense to you, then you're there. Rest is just syntax after this. Okay, perfect. Very good. Okay, cool. So let me show you how this actually works. We substitute these two variables. What I'm going to do now is I'm going to declare a few things that I need to solve this. So remember we saw in that sine wave example, we have to declare a time step and we have to declare a time array. I'm doing the same thing. So in line 9, I will say dt, which is my time step. I will say it is 0.1 seconds. It's a very small time step. Okay, so I can sample very frequently. Then I will say time equals 0 colon dt colon 50. So I will simulate my system from 0 to 50 seconds. And whatever is the length of this array of time, which I know will be 501, I will store it inside a variable called n, because I will use it again and again. Okay. Then in line 15, what I say is x1 equals zeros of n comma 1. So this will just generate a long vector, which is just filled with zeros. So it will have only one row and it will have 501 columns. Or I might have got the rows and columns flipped. That doesn't matter. It doesn't matter. The point is I have just allocated an empty array, which is just filled with zeros. And as I keep on computing the solution, I will keep on filling the values one by one. Same thing I do with x2. So x1 stores my displacement value. This is on line 15. And on line 16, x2 stores my velocity values. Right now, initialized everything with 0. And then I'm going to just keep on adding the values into the vectors. And initial conditions, I always have to set the first point, right? Because I have to start from somewhere. So I say x1 equals 0 displacement, x2 equals 0 velocity at the first time step. That is what these two lines of code say. Is that clear so far? Yeah, x1 and x2 are both unknown right now. I only know the first point of them. Okay, so the next section is a little bit tricky, but if you can grasp it, then we are fine. Then we have achieved our goal for today. So I think most people are following anyway. In case you can't follow it, you can do that ODE course online. It will take a longer time and explain these things in detail. Okay, right. Now we have to understand these three lines. And if we understand these three lines, then everything is fine after that. So I will say for any particular time step of I, called I can calculate my acceleration using this equation. What is this equation? It is nothing but what we had up here. Mx double dot equals f minus kx minus bx dot. So I will say, I know what the value of force is, minus k, I know what the value of k is, and I will say x1 of I minus 1. So at the last instant, okay, at the last time step, what was the value of displacement? Multiply that by the spring coefficient, that will give me my term. Similarly, minus bx2 of I minus 1. So what was my value of velocity at the last instant? Just multiply it by damping. That will give me another force term. So I add and subtract all of these force terms, divide the total by mass, and that will give me acceleration. Okay. Now, if I know my acceleration, how do I get from acceleration to velocity? I have to integrate it. So what do? I say my velocity at time step I, which is right now, is equal to the velocity at the last instant plus acceleration times dt. So acceleration times the time step, that is the change in my velocity, I added to the last velocity I had. And similarly, once I know the value of my velocity, I can also say whatever was my last displacement, take the velocity multiplied by the time step and add it. That will give me the current displacement that I have. Okay, so this is actually a kind of manual integration that we're doing. And this is known as the Euler's method for solving ODEs, which is a first order method. There are also more complicated methods like Runge-Kutta method, fourth order, Dorman-Prince, fifth order. But this is the first order method. It's the easiest to write. Okay. There's a question, why do you not double equal the condition here? Because I am actually assigning this value to this variable. I'm not declaring an equality. Okay. So forget about the symbolic math syntax. That's a different subject. This is just normal addition, subtraction equal to.
Can you explain the third equation?
This one?
Yes.
Yeah. So what is my term x1? X1 is displacement. Okay. So I say, what is my present value of displacement? Well, I will just take the last value of displacement plus velocity times dt. Okay, so this is nothing but v equals u plus dt. It's the same thing. Or the same thing in displacement. So that is the v equals ut term. This is the s equals last displacement plus velocity times time step.
Sir, in the second equation, won't we be taking the this velocity at the last?
So you want to use I minus 1 here? Hello? Yeah, so if you want to take the velocity at the last time step, yes, you can do that. You just do I minus 1. It is almost like a matter of preference which you want to do, but what we assume is the error is kind of negligible if the time step is small enough, because the change is actually quite small. So if you want to use I minus 1, the result will be basically the same. It depends on what the problem is. I suppose I minus 1 is technically correct. Yeah. Okay. There's a question, how can we decide which numerical method to choose? I'll cover that shortly. All right. So if you have gotten this far with me, the conceptual heavy lifting is done. After that, it's literally like 3 lines of code to solve this problem.
Excuse me, sir.
Yes.
So I minus 1 is basically I minus dt, right? Like we are just moving one point before the ith point, like dt point.
Yes. Yes.
Okay.
Yeah. Okay. Right. So what I have to do is I just open a for loop.
So AT means velocity. How it?
That is your 9th standard physics. Velocity equals acceleration times time.
So sir, it should be like integration of this with respect to t.
This is integration with respect to t. Okay, let me explain it here. Okay. Do you understand this equation that you studied in your 9th class? Yes, no?
Yes, sir.
Yes. Yeah. So what does this mean? If I have a graph and I know this is time here, okay. So if I know my velocity at this point, so this is my velocity u. I know the rate of change of velocity. Rate of change is nothing but gradient, right? So that is a. And I take a time step of dt. right? So what is this point going to be? Can you tell me?
U plus ADT.
V.
Yeah. So this point is going to be V, which equals U, which is this level, plus A, which is the gradient, times dt. So this change, which is here, is, sorry, that should not be a 3, that was a bracket. So this change that you're getting here is basically A times dt. Okay, because the rate of change is acceleration and the time step is dt. Now this is how integration works. This is integration. The assumption in integration is if you make your dt infinitesimally small, this is actually integration. So numerical methods always have a small error, but if you make your time step small, it will still give you small curve. Does that make sense, people? Okay, I guess some people have got it and some are a bit lost. I can have another try explaining. If you what is your doubt? Just tell me. You're muted if you're talking.
I guess all of us understand this thing. May the original student who was having the query can answer. Otherwise, like all of us understand this.
Okay.
Yes, I got.
Okay, perfect. Right. So from here, all I have to do is literally convert these 3 equations into MATLAB code, which is very, very easy because MATLAB is designed to do mathematics. So I just say for I running from 2 to n. So n was the length of my vector. I say acceleration equals f minus k x1 of I minus 1 minus b x2 of I minus 1. So x1 is displacement, x2 is velocity, and divide the whole thing by mass. If I know my acceleration, I can say my current velocity equals last velocity plus a times gt, and current displacement equals last displacement plus velocity times dt. Now, if you are not happy with these indices, you want to do it all at the same time step, previous or current, that is fine. You can rewrite the code that way. It won't make much difference. Anyway, when I run this code, oh, I didn't run the previous section. So just make sure you run this section. When I run this code, this system is solved. And all I have to do is plot it out to get the solution. So I plot with respect to time the values of x1 and x2. x1 is displacement and x2 is velocity. Okay, that's literally it. That's all it needs to solve an ODE. All right. Now, if I want, I can go and make the same changes in the parameters up here. And if I run this all the way to the end, I'll get the same result exactly that I got with my analytical solution, right? So I know my numerical method and my analytical method are giving me the same solution. Therefore, it's probably right. Or we know it's right in this case. Okay. There's a question, why using I within the loop when I is used to? Yeah, you have to go and study your basic programming. Do the MATLAB on them. This is basic stuff you should know. All right, so let's take a 5-minute break. We'll come back and take any questions. Then I'll tell you about what the inbuilt solvers can do. And then I'll show you Simulink quickly. The app, we might have to wait a bit, okay? Because I really want to show you Simulink and Simscape because it's like a superpower for engineers. Most people don't know about it as well. Right, so I'm going to put a 5-minute timer here. And just, go use the bathroom, have some tea, coffee, whatever, and then we'll come back in 5 minutes. Okay, yeah, if you can all come back now, please, that would be great. Okay, so please put any questions about this stuff so far, because we're about to move on and do some more complicated stuff now. Any doubts so far? There's one question: when making use of MATLAB, or how to make use of MATLAB library when learning, especially we have to do some animated simulation graph like contour plotting. Just go and look at the documentation. So if you're generating plots inside a for loop, it will get, it actually gets populated in real time, and then you can replay that simulation as well. So if I take all of these plot commands inside this for loop, okay, and suppose I run this, you will see it happens automatically. So it will look a little bit weird because it's not set up properly, but it should still work. Now, one thing to understand about plotting is it will heavily slow down how fast the computation happens, because plotting takes up a lot of visual memory and compute time from your machine. Okay, if this runs in the next second, then fine. Otherwise, I'll skip this for now.
Hello, sir.
Yes.
Sir, from where you can get all these lectures, are like from basics to everything, like all the course type, to study perfectly from basics?
Okay, yeah, you guys don't really read the emails, right? That's the problem. So I'm going to repeat this again, and then again if you want. So there are two links that you, or three links you have to keep in mind. So first thing is you go to matlabacademy.mathworks.com, go to getting started. And in this place, we have all of the on-ramp courses. So they take around 2 to 3 hours each, and they will teach you the basic concepts. Okay. So there will be MATLAB, Simulink, Simscape, all of these, image processing, signal processing, machine learning, everything is there. This page. Okay. Now, if you want to go to the mathematics part of it, then you can go and look at the math and optimization. So everything that we have discussed today is here. Symbolic maths, ordinary differential equations, linear algebra, everything is here. Just do the courses. Second thing is go and look at the videos page on the MathWorks website. So you can see we have more than 4,000 videos here. I'll just copy and paste this. You can just bookmark these two links. So suppose you want to learn solving ODEs with MATLAB. Sorry, messed up my search. Solving ODEs. And you will see a bunch of videos will actually come up in the search. So you can see there is solving ODEs in MATLAB, Euler ODE1. If I click on this one, it will take me to an entire series of lectures where everything is explained in detail. Okay. So this series will have Euler method, midpoint method, Runge-Kutta method, estimating error, ODE45. Everything that I'm discussing today, it's already online. Okay. So just go and look at the resources. Can we solve 5-parameter model also? Yeah, you can have, I mean, the models we solve have thousands of parameters, so you can keep solving. Right. Now, this next part, we are not going to do it hands-on because we don't have time. I'll explain it to you and you can run the scripts yourself. So I want to talk about what ODE45 is, and this will just be more of a lecture. Then Simulink models you can open hands-on. So while I'm talking, just open up the Simulink SM01 model, and I'm going to tell you what the ODE45 actually does. And you can look at the code yourself in this ML03 script later on. So suppose that I have to solve some system of ODEs inside MATLAB. Okay, so I have a y-axis, then I have an x-axis, and some, I'm plotting some signal here, and this is the time vector here. Okay. Now suppose the actual solution of my system looks something like this. Okay. So that is what my system actually is looking like. Now, let me zoom into one of the parts here. Sorry, just trying to locate it properly. Okay. Now let's look at this region where there's some change happening. So suppose that I select a point. Let me select it with this green color. Suppose I select a point, and after a time step of dt, I want to find the value at the next point. Okay. Can anybody tell me how I get from here to here? We just covered this.
Multiplying the slope of the curve with the delta.
Okay. Yeah. So I get the slope of the curve at this point. I integrate it with respect to time. Okay. So I integrate with respect to time of dt. So that's my dt. And I try to get the next value. Now what will happen is, because numerical methods are not exact methods, they're approximations. So if I use an Euler method, my value is going to end up somewhere like here. Okay, so I have an error. That is going to be my error. Now what that means is the only way to reduce this error is to reduce my time step. Okay. So what happens is, for large systems, when we are doing a lot of computation and your system is changing rapidly, your time step becomes so small. It becomes 1e to the minus 6 that you will have to do millions of computations per second or per second of the system's behavior. Okay. So to adapt to this, we came up with some more methods. Okay. So there are two methods you should know about. One is called the Range-Kata method, and the other, then I'll talk about ODE 45. So just tell me yes or no in the chat. How many people know what a Range-Kata method is? Fourth order method. Yes or no? Okay, some people know it, some don't. That's all right. Okay, I'll just tell you. So basically what a higher order method means is that, suppose I have this curve. I'll draw a separate one to avoid messing up this one. Suppose I want to match closely to what this curve is doing. Okay, I want to match my behavior. So instead of just taking this one point and looking forward, what I will do is I will take 4 points for a fourth order method. So I will take this point, this point, this point, and another point. And what I will do is I will compute the overall kind of curve that fits through these 4 points. And that curve will look something like this. Okay. So if I have 4 points, that is going to give me a much more accurate line than just having 2 points. So when I plot this point here, in the next time step, this error is going to be a lot smaller. Okay, so fourth order method will typically have a smaller error than a first order method. And what that means is I can use a larger time step. Okay, so if I want to use a ODE 4, which is Range-Kata method, I can use large time steps of dt, and I will still be able to get good solutions. That is why we use these fourth order ones. But what happens after that? Again, you can come back and watch this video later on also if you're confused. After that is, even with fourth order, if a system is changing very fast, like here in this region, it's changing very fast, I need to have small time steps. Okay, so let me draw a few things. Oops, that's not working. So I need to have small time steps in this region. Okay, because the rate of change is still fast. But in this region here, I can get away with a large time step, right? Because there is hardly any change between these two regions. So here it is fast rate of change, and here it is kind of slow. I'm sorry about the pixelated stuff. I'm quite zoomed in here. So what happens is we use combined methods where we have a fourth order and a fifth order method, and we compute both solutions at the same time, and we vary the time step dynamically depending on how fast the rate is or how much the error is. So when we say ODE 45, that is not a 45th order, that is actually 4-5 order. It's a 4th order solution and a 5th order solution. Okay. So what happens is, where should I draw? Let me draw here. So if I'm sitting at this point, when I calculate the 4th order solution, it will be here. Make it a little bit cleaner at least. There. And if I calculate a 5th order solution, the value will come down here. Okay. And because of the way mathematics is, the 4th and the 5th order solution, the odd even solutions, they will always be on opposite sides of what the actual solution is. Can anyone tell me why? Can anyone guess? I'll tell you in a second. Okay. So where all the stuff. Sorry, could you repeat, please?
It is because of the curve fitting, like x square versus x cube. One is coming positive, another is coming negative.
Yeah. Pretty much. Okay. So roughly speaking, it all comes out of Taylor series or patterns of maths similar to Taylor series. So I hope all of you have heard of this term Taylor series. You can go and look it up on Wikipedia afterwards if you have not. So even inside MATLAB, right? When I say sine of this point, MATLAB doesn't know by magic what sine means. What it will do is it will actually break down that function into this kind of approximation. Okay, so the value of the function at a plus the rate of change times some coefficient plus the second order differentiation times the coefficient squared, like this. And for a sine wave, especially the way the mathematics works, let me find the correct one here. Just give me 1 second. Okay, so this graph actually explains it perfectly. Okay, so what happens is the lower order solution will give one result. The higher order will fit to the upper side of it. For most of them, this exponential function is kind of weird. So the 4th and the 5th order solution will give you basically points on different sides of the curve, generally speaking. Even if it doesn't give different sides, it's still fine. It will still work. So what we do is we compute the difference between the 4th order point and the 5th order point. Okay, so my 4th order point is here, my 5th order point is here. I get the difference between them, and that difference is called the error. Now, what I do is, if the error is small enough, it is smaller than some threshold that I defined, I will keep my time step and I will continue climbing up this curve. If the error grows too large, then I will compress the size of my time step. I will reduce it such that I can save the computational time. And when I get to a flat region, I will expand my time step. So what the ODE 45 does is it basically gives you lots of points when the curve is changing fast, and it gives you much fewer points when the curve is changing slowly. So it creates a balance between the accuracy of your solution and how much time it takes to get that solution. Okay, I've explained this at a very high level. If you want, the scripts are there. So the ML03 script will explain how to use ODE 45. You can also type doc ODE 45. This will open the documentation and you can read here. There are many examples. And there's also a section which tells you how to solve different kinds of problems. So especially if I look at what is known as a stiff kind of ODE, this is a van der Pol equation. If you can see my screen, what you will see, this ODE changes very rapidly at certain points. So at a place where the curve is smooth, you have fewer points. And where it is changing very rapidly, you have a lot of points. So this way you can change the time step dynamically to make sure your computation is efficient. That is what ODE 45 and all of the other solvers inside MATLAB. Okay. How is the actual solution being chosen between 4th and 5th order? You can always choose the fifth order. Fifth order is always better, but the point is to compare the error between them. Okay, so just go and read up on that a little bit, and you will find lots of resources on this out there. All right. Okay, so what I'm going to do now is, I hope you've been able to open up the Simulink model. I'll just show you how Simulink works in like 5 minutes. And if you want homework, your homework will be to go and do the Simulink on-ramp. So let me show you why Simulink is so powerful. So if I have a system of ODEs, actually, let me tell you what Simulink is. So inside Simulink, what we do is we basically drag and drop different blocks into this canvas. And then we can solve the system very quickly without writing any code. So let's say I have a sine wave. This is one block. And then I have a scope. This is another block. And I kind of link them together. Okay, so I take the output from the sine wave block and I input it into the scope block. Scope is just a display block. And I run this. What I will see is what the output from this model is. It is directly plotted here inside the scope. Okay, so I don't have to write any code. I just pull in the mathematical functions, integrate, differentiate, whatever I want. I'll get the result directly. And what is running in the back end of Simulink, if I go to modeling and then model settings here, is Simulink comes with a bunch of built-in solvers. Okay, so if I look at the solver details, you can see ODE45 is built in along with a bunch of other solvers. So there are solvers for stiff systems, for BAEs, etc., etc. So ODE45 is the default solver in Simulink. And what this means is I can just define a differential equation directly here, and Simulink will solve it just by magic. You don't need to set up all the states and display this and display that. So suppose I had to solve this mass spring damper system. Let me show you how easily I can do that. Okay. First thing I'm going.
Dr. Chandra, sorry to interrupt you. There is some problem. Actually, we'll have to close the session at 1 itself because this ID is getting used with some other meeting from 1 to 2. We were like.
Right.
Okay. That and we can like because you are starting a new topic, we can extend it from 3 to 5 session.
I'll tell you what, let's postpone it, and people can go and look at the Simulink on ramp. Okay, because the second session we will have another topic.
Yeah, that would be good. That would be good. Yeah, just sorry for this. Sorry.
No, it's okay. It's okay. Okay. So okay, we have 2 minutes. Were people able to generally grasp what ODE45 means, the fourth and fifth order stuff?
Yes.
Yeah, if we got that far, it's okay. Great. So your homework, please, is to go and do the Simulink on ramp, and the stuff that it will teach you. Believe me, it will be very useful. It will. If you're working with ODEs, it will speed up your work by a factor of 10 probably. All right. Great. So I think we can close the session for now and meet back at 3 o'clock. And then we'll talk about curve fitting, optimization, machine learning, that stuff.
Yeah, definitely. So thank you. I'd like to thank the speaker and the MathWorks team, Dr. Dhruv Chandel, Dr. Vipul Pandey, on behalf of the student community. And we'll end this session for now. Sorry for that. And then we'll start from 3, the session 2. Okay. Thank you all for joining in.
Great. Thanks a lot. Bye.
Yeah. Thank you.
Thank you, sir.
Thank you.